Today's lesson, we're going to start looking a little bit more at the periodic table and learn a little bit more about how it's organized. So the elements weren't just put in any particular order. They're put in order based on their atomic particles and properties. But because of that, you also see a lot of other patterns appear. So what we're going to do is look at something called trends on the periodic table in the next two lessons. If you hear the word trend, it really just means a pattern or something that you can see that's consistent throughout different areas on the periodic table. So we're going to look at three patterns today. One is with atomic radius, the next is ionization energy, and then the last one's electron affinity. And we'll go over what all of those mean so you can understand those terms first before we look at the patterns. So the first one that we're going to take a look at is atomic radius. This is probably the easiest one to understand, especially with the background knowledge that you have. So atomic radius is basically talking about the size of the atom, the distance from the center of the nucleus to the outside of the last orbit or orbital of an atom. So just think like a circle or a sphere in math. You've got the center there, that's your nucleus for the atom, and it goes all the way to the outside where you would find that last electron. Because atoms are really, really small, the unit of choice when you're looking up tables that give you the radii of different atoms, it's in something called picometers. So meter we're all familiar with. Pico means it's a lot smaller. A lot smaller meaning 1 times 10 to the negative 12. So it's a really, really, really tiny number. But when we look at it in picometers, it's a little more manageable. You don't ever have to memorize any of the atomic radii of atoms, but here's a couple so you can compare. Sodium has a radius of 186 picometers, where magnesium is 160 picometers. So you can see there's a difference in size with those atoms, and we'll try and go over and explain why that happens. So what's our trend or what's our pattern when we look at the periodic table and think about atomic radius? The trend is it decreases as you go up and across the periodic table. So when we say up the periodic table, we mean bottom to top. And then across means we're going left to right. So in general, why is this happening? When we go from bottom to top, we can see the atomic number decreases and we're going up different rows. Each row approximately looks at an energy level for the first few elements that are there. So if you think about Bohr-Rutherford diagrams, Bohr-Rutherford diagrams have different circles or orbits, and they each represent an energy level. So if you have less electrons to place in them, you're going to have fewer energy levels, and then the atom itself is going to be smaller. Remember, atomic number tells us how many electrons are in the atom. So as we're going up, there are fewer energy levels. And that makes a smaller radius. As you're going across from left to right, and when we say across, we're trying to stay horizontal within the same row or the same period on the periodic table, the radius also decreases. But it's a slightly different reason why that happens. So if we were to, example, go from lithium to neon, they're all in the same row, so all of those electrons are in the same energy level. Lithium has number 3, where neon has number 10. So yes, there are more electrons. That might be your first thought in neon, but remember, atomic number also tells us number of protons. And we know protons have a positive charge. So if there's more protons in the nucleus, what happens is there's more positive charge. And more positive charge means it's going to pull the electrons into the nucleus, or closer to the nucleus, not into it, a little bit more tightly. And it shrinks the atom as you go across. Yes, there might be more electrons, but remember, electrons are super tiny compared to protons. So as you're going across left to right, there are more protons. This creates a greater pull on the electrons, and then that makes a smaller radius. So let's try and put this in context with a couple of different atoms. If you want to understand this better, we're going to use Bohr-Rutherford diagrams. So if you need to review that before we do this part of the lesson, that might be something you want to think about going forward. All right, so this question says, arrange the following atoms in order of increasing atomic radius. Increasing means we're going to rank them from smallest to largest, and we're going to try and explain our choice. So we have chlorine, neon, and scandium. So the first thing that I would do if I was tackling one of these problems, I'd want to figure out where are these elements on the periodic table. So I would take my periodic table out and kind of map out where they are. I've got a blank one here for us to talk about it all together. So if we take a look, scandium is here. We've got neon up here and chlorine over here. So now I can see where my elements are located on the periodic table. Next thing I want to do is think about the trend. So with our trend, we said we're always going to go in the same direction, bottom to top and left to right. We said that if we follow this pattern, the radius decreases. So if the radius decreases, if we're going up and we're going across, the larger atoms are down here. And as we go up and across, the smaller ones are up here. So just by the placement and knowing the pattern, we can get the order. So smaller ones up here, larger ones over here. If we follow that pattern, that would mean neon's the smallest, then chlorine, and then scandium. Okay, so right now we've got our order. Okay, so usually ranking them, if you know the pattern, is the easier part. We just want to try and explain now why that's happening using some of those ideas that we just talked about. So what I would do now, pause your video and see if you can draw 3 different Bohr-Rutherford diagrams for each of the 3 atoms. And once you have those drawn out, unpause your video and then we'll look at them and try and explain what's going on. All right, let's check out those Bohr-Rutherford diagrams. So I've got 3 here, and I'm going to just reorder again what we've got up here to answer the question for reference. So why is neon the smallest, and why is scandium the largest? Visually looking at them, you can see that neon only has 2 energy levels. So you can see that its radius is going to be smaller. It has the fewest number of electrons as well, but only 2 energy levels. When you look at chlorine over here, it has 3 energy levels. And when we look at scandium, 1, 2, 3, 4, it has 4 energy levels. Now this one's also one that's a little bit of an exception, something you'll learn a little bit more later on if you take grade 12. But the last energy level here is energy level 4. So comparing these 3 and having their Bohr-Rutherford diagrams, you can see right away visually the number of energy levels decides the size. Neon's the smallest, followed by chlorine, then we get to scandium. Let's look at another trend now together and see if we can start to make some more sense of the periodic table. The next trend that we have is ionization energy. So what does it mean? It says it's the amount of energy required to remove an electron from an atom or ion in the gaseous state. So basically what that means, if we use this general example here, here is your element. Okay, it's not an ion, just an atom as an element. And it should be in the gas state for this to happen the most easily. You need to add some energy. Here, plus energy means you're adding or using energy. When you're doing this, you're using that energy to remove an electron. So here's the electron that was removed, and now you're left with an ion. And it's a positive ion because you can see the positive charge. So ionization energy is the amount of energy that's needed to remove one electron from an atom. Just as an example, so you can see a number, if you did it for lithium and you removed one electron from lithium, which you see over here, it forms a positive ion, and it requires 520 kilojoules of energy per mole. Mole is a unit we'll learn about later on, but it helps with measuring and understanding amounts in atoms and compounds. One thing to note, if you see a larger ionization energy, means it's harder to remove the electron from an atom or an ion. So bigger number means harder to take it away. So back to, well, why is this happening and what's the trend? The trend here is it increases as you go up and across the periodic table. So here the trend is getting larger. Why is this happening? So remember with atomic radius, we said there are fewer energy levels going up. That is true here, and that's part of our explanation. But we want to look at it a little bit differently. If there's fewer energy levels, that means the electrons that are on the outside of the atom in that last orbit are going to be closer to the nucleus. We call those ones valence electrons, if you remember that term. And if those valence electrons are closer to the nucleus, that means they're closer to the protons. And remember, protons are positive and they like to attract electrons. So as you go up, they might get smaller, but those electrons that you have to remove are closer to the nucleus and closer to the protons. So it's going to take more energy to pull away those electrons and make the ion if they're closer to the nucleus. Going across, again, we're looking at a similar point of view from atomic radius, but with a change. This time we're looking in the same row, but the number of protons increases because the number of the atom, the atomic number, also increases. Okay, so that hasn't changed. But here we're looking at it again, slightly different viewpoint. Here, if there's more protons, it means more pull on the electrons. So it makes them harder to remove. So as you're going across, we're staying in the same energy level, but more protons. Over here, there's a lot more pulling the electrons. So if you're trying to remove it, it's going to take more energy to do that. So we're going to do another problem similar to the first, try and rank some elements in terms of ionization energy, and then explain why it's happening. So here are our elements, and here's the question. This question says we want to put them in order from smallest to largest ionization energy and explain our choice. So we've got silicon, oxygen, and sodium this time. So just like last time, you want to try and find where those elements are on your periodic table first and see if you can make some sense as to the order, and then we'll look at why it's happening. So taking a look at your periodic table, you want to find those three elements. Here's sodium, here's silicon, here's oxygen. So those are your three elements. Our trend, we said ionization energy is going to increase when we go up and across. So highest amount of ionization energy is going to be up in this area, and lowest will be over down here. So if we're trying to rank it from smallest to largest, over here sodium is going to be the smallest. We're going across, this is in the same row here. Silicon is next. And then the hardest over here, the largest is going to be oxygen. So based on their placement and the pattern, we can put it in the right order. But again, it all comes down to what can you actually explain. So at this point, again, just like last time, what I want you to do is pause the video and try and draw 3 Bohr-Rutherford diagrams, one for sodium, one for silicon, and one for oxygen. Once you've drawn those, you can unpause, check the diagrams with what we have in the lesson, and see if you can explain as well what's going on. Okay, so let's put these in order. We said smallest to largest ionization energy. So it was sodium and silicon and then oxygen. Here are the Bohr-Rutherford diagrams for those 3 elements. So now we want to try and look at, well, why is oxygen having the highest and sodium having the lowest? So first of all, let's look at oxygen. Oxygen out of all the 3 is the smallest. So that means the electrons are closest to protons. So it's going to be the hardest to pull them away. Okay. So right away you can see these ones are smaller. These electrons, one of these ones is going to be pulled away. Maybe it's this one. It's only 2 energy levels away from the nucleus. If you compare silicon and sodium, there's 1, 2, 3 energy levels. So that outer electron, whether it's this one or whether it's one of these ones, they're further away, so they don't feel the protons as much. The other energy levels kind of shield them from that. When we look at sodium and silicon, they're both in the same period, the same row on the periodic table. So you can see they're both ending in the 3rd energy level, but what's the key difference here? Sodium has 11 protons versus silicon has 14 protons. So even though the electrons are in the same energy level on the outer shell, energy level 3, since silicon has 14 protons, it has a stronger pull compared to sodium here. "14 electrons to pull those electrons, where here there are fewer electrons and fewer protons, only 14 there." So hopefully that helps understand a little bit more about why you see some differences in the elements with respect to ionization energy and the pattern on the periodic table. One more trend for this lesson is something called electron affinity. This one is very similar to the others in terms of explanations, but understanding what it means is a little bit different. So here, electron affinity means we have an electron that's being added to an element. Okay, this time we're forming an anion. So it's kind of like the reverse of ionization energy. Instead of pulling one off, we're adding an electron to it. And since we add electron, it's going to become negatively charged. Here we're also measuring energy, but this time it's an energy released during the process. So if we look, here's our element, neutral as an atom. Here is the electron that's being added. Okay, so you're adding that electron. It makes your anion, and then some energy is released. When it's on the right side of your arrow, it means released. So we're trying to look at this amount of energy here, and this is where it can be a little bit trickier to understand. So if you're looking at the energy here, if it's a higher amount of electron affinity, meaning more energy released or higher amount of energy, it means the atom is more likely to gain the electron. It means it's more stable. The energy isn't need to be held onto because adding electron actually stabilizes the element when it forms the ion. So it says, I don't need to keep the extra energy, I'm going to get rid of it. The energy is basically not needed, so more will be given away. If it wants that electron, it's going to take it, and then that energy is not needed, so it gives it away. Oppositely, if you see a lower value for electron affinity, that means less energy is released. So if you don't give away the energy, that means you need to keep it in the ion. And the ion needs to keep it because it doesn't really tend to want that electron on its own. It would rather give it away, but if it's being forced to do that, it's saying, well, if I have to keep it, I need extra energy to be happy. So this means extra energy is needed in the ion to be stable, so it only releases a little bit. In terms of values for electron affinity, when you look at the periodic table, this one's a very, very general trend. There's some good patterns with metals versus non-metals, but there are some exceptions along the way. So this trend is one that's a little bit more general versus specific compared to the other two we've seen so far. In terms of pattern, we're still going to look going up and across. That hasn't changed. We know it increases. And we still want to think about those two different things. As we go up, there's fewer energy levels. And going across, there are more protons. But the other thing that you can look at is what types of elements are present, because that can also play a role. So if you remember from your review, you have this staircase that goes down the periodic table. On this side of the staircase, you have metals. And then on this side, there are non-metals. Metals, when they form ions, would rather be positive, and non-metals would rather be negative. So here with electron affinity, remember we're trying to make a negative ion. If we know non-metals tend to want to be negative, they're going to try and take that electron more likely, Versus nonmetals, they'd rather be a positive ion. So if you're forcing them to do the opposite and become a negative ion, they're not very happy and it's not as likely to happen. So that's why they need to keep more energy, and that electron affinity is lower, the amount that's actually released. So let's take a look at the last practice problem. So you've got 3 elements, and we're going to put them from largest to smallest electron affinity: carbon, fluorine, and potassium. So we want to do the same thing like we did with the other 2 problems. Take out your blank periodic table. Think about the trend. We know up and across electron affinity increases. And we're going to try and find those elements on the periodic table. So potassium's over here, carbon is over here, and fluorine is sitting right there. So if we want to rank them from most to least, or largest to smallest, our largest one here is going to be up at this end of the periodic table, which is fluorine. Then comes carbon, and then comes potassium. It's going to have the least amount of energy released or the smallest electron affinity. But again, now we want to try and think about why. Thinking about, do we have metals or nonmetals? And what does their electron arrangement look like in Bohr-Rutherford diagrams? So last time for you to pause the video, draw the Bohr-Rutherford diagrams, and see if anything pops out at you. Can you see why an atom might want to accept the electron versus not accept the electron? Look at its structure and see what you think. Hopefully you've given this a shot. So let's take a look first at the Bohr-Rutherford diagrams, and we'll just rewrite our order here. So we have fluorine, carbon, and potassium. This had the most or highest electron affinity, and this had the least or the lowest. So first let's look at potassium. Potassium here is a metal. Compared to the other 2, carbon is nonmetal, and so is fluorine. So we know metals prefer to be positively charged when they form ions, and we know nonmetals prefer to be negative. So right away, this is one thing you can say. Metals don't want to accept electrons. They would rather give them away. They don't want to keep their electrons. Okay. These ones want electrons. So if we look at potassium, we've got all of these energy levels, and now we're saying we want to add an extra electron to this outer shell. This would be adding. So if we were to add it, we would add it to the last energy level here. And there's a couple things you can look at. One, here you've got an electron that's by itself. We're adding another one in here. It's unpaired, it's not exactly balanced, so it might not want it. All of those protons are sitting also in the nucleus, and if it wants to attract that electron, there's a lot of different energy levels and electrons blocking its path to feel that positive charge there. So it would rather not keep it. The size of the electron is large, size of the atom is large, and it doesn't feel those protons at all. When we compare the other 2, fluorine and carbon, they're both in the same period, both in the same row on the periodic table. But here, if we look at fluorine, fluorine has almost a full outer orbital. Over here, there are 7 electrons. So if we were to add an electron, it would go in here and it would pair up. So it makes 8. And when it's full, it makes it more stable. So forming an ion, it would form the fluorine -1 ion called fluoride ion. This is very stable and actually makes that element very happy. So it really wants that electron. When we look at carbon over here, carbon has only 4 in its outer shell. If we were to add another one, extra one here, it's unpaired. So it would take it, but being unpaired makes it a little bit less stable. It's only a couple energy levels away from the nucleus, so it'll still feel the protons. But if you compare it to fluorine, carbon has fewer protons. It has 6 protons. Fluorine has 9 protons. So that extra electron is pulled in, but not as tight as the fluorine as well. So those are some things that you want to think about when you're explaining the trends. Looking at the trends and getting the order is the first thing that you want to understand and be able to do. And then once you're comfortable with that, the next thing that you want to do is look at energy levels, look at the nucleus and protons, and look at the type of element that you have.